Assalamualaikum and good morning. Today I'm going to present on how to solve first order ODE equation. So there are two types of solution for first order ODE equations. There are analytic solution and there are numerical solutions. So before I show the numerical solution, I'm going to show the analytic solution first. For analytic solution, there are two cases for non-separable ODE and separable ODE. But in this case, we have this equation, and this equation is a non-separable ODE. So for non-separable ODE, we have to introduce the integrating factor on both left-hand side and right-hand side, and then you have to differentiate the equation, and then you will get this x3, and then you integrate it and you will get this, and then solve and you will get the y for the equation. So this is the final solution for the y. And then if you want to get the exact value for both x and y, you have to choose a value. For an example, for x 0, 0.1, 0.2, 0.3, and you just have to substitute with the x in the equation. And when you do that, just calculate it all of it, and you will get the exact value for y. Moving on to numerical solution, we have three types of numerical solution. The first one is Euler method, and then improved Euler method, and then Runge-Kutta method. So we are going to look into Euler method first. Okay, Euler method is one of the most simple method out of all the three. So let's say we have this equation, dy over dx is equal to negative 2y plus x cubed e negative 2x. With y 0 is equal to 1, x is equal to 0 0.1, 0 0.2, 0 0.3, and h is equal to 0 0.1. So this is the formula for Euler method. Fx is equal to x, fxn yn is equal to, this is the equation that we are solving. You have to just substitute the y and the x with the xn, yn, and then the yx plus 1 is equal to yn h plus fn. So let's say we are trying to find f naught, f0. So we have the value of x naught here and y naught here. So x naught is 0 and y naught is 1. So to find f naught, we have to just substitute this 1 with the value of x naught and the value of y naught. So 0, 1, and then you have to also substitute in this equation that we have here. And then after that, if you want to go and find the value of y, you have to substitute the y naught plus dengan h and also the f naught here, and then you will get the value of y. So this is the value that I have calculated before. So the y naught is equal to 1, y1 is equal to 0 0.8, y2 is equal to 0 0.6400818873, y3 is equal to 0 0.5126017545 from respective x, 0, 0 0.1, 0 0.2, and 0 0.3. Okay, so now moving on to the improved Euler method. Improved Euler method is not the most accurate method, but it's also more accurate than Euler method. But Runge-Kutta method is more accurate to improve Euler method. So the y value of Runge-Kutta method is like almost the exact same with the exact value that we get from the analytic method. So we are still using the same equation, which is the dy dx is equal to negative 2y plus x cubed e negative 2x. So the x naught and the y naught value is still the same, but the formula is a little different from the Euler method formula. Instead of trying to find f naught, we are trying to find the k now. So the formula is k1n is equal to fxn yn, and then negative 2yn plus xn 3e negative 2xn. This one is also from the same equation. You just have to substitute the y and the x of the equation with the xn and yn. So let's say we are trying to find the value of y1 with the x naught and the y naught. So this is k10, and then you just have to put the value of x naught, which is 0, and then y naught, which is 1, and then is equal to -2 y 1 plus dengan x naught 0, 3 e -2 and another x naught here. So if you calculated the ky0, you will get a value, and then move on to the k20, f xn plus h. This time we have to plus h, and then yn plus h, and then you have to put in the value of k1n that we just get from this equation, and then -2 yn plus h kyn, also have to use this value, and then plus xn plus h 3 e -2 xn plus h, and then the y1 value is equal to y0 plus h over 2 k 1n, this value that we calculated, and also for the k2n we have to plus both of these here. So from the value that I get after calculating from the respective 0, 0.1, 0.2, 0.3 x, we have this y is equal to here y1, y2 and y3 value. This is one of the example on the range quota method. So this time we are going to try to solve and get the value of y3. So our value of n has to be 2. So this is the first one, k12 is equal to f to the power f x2 y2. The x2 and y2 value has been calculated before, so you just have to substitute, and then substitute also with the equation, and then we will get this value. And same for the k22, and then on the k12 that we have to substitute in the k22, just take this value and it goes on the same until k42. And then lastly for y3, we will have to use y2 plus h over 6 in bracket all of the k that we calculated before, and then you will get the final answer for y3 value. Moving on to the third solution for third method for numerical solution, which is range quota method. This is the most accurate method to get the y value. So the solution for this, the formula for this range quota method is a little bit complicated. So the k 1n is equal to f xn yn is equal to -2 yn plus xn 3e -2 xn. We are still using the same equation, so the structure of the equation will also be the same. And then for k2n, they have to substitute xn plus with h over 2, and then yn plus with another h over 2 with the k1n that we get here, and then -2 yn plus h over 2 k1n plus with xn plus h over 2 to the power of 3 e -2 xn plus h over 2. So this also continue with the k3n, except for the substitution will be with k2n instead of k1n. And same also for the k4n. F is xn plus h yn plus h k3n is equal to -2 yn plus h k3n plus xn plus h to the power of 3 e -2 xn plus h. The n also has to have a value. For example, we use x naught and y naught, so the value here is going to be 0, 0, 0, 0, and this one is going to be the value of y1. And then the final one to have the y value is equal to yn plus h over 6 plus with all the k that we have calculated here. And now from all the calculated value from Euler method, improved Euler method, range quota method, we already put everything in a table using the same value of x, which is 0.0, 0.1, 0.2 and 0.3. but two different value of h. For Euler method, we have h is equal to 0.1 and another h is equal to 0.05, and so is for another two method. There's a improved Euler method with both the same h, and Ranch-Kutta method with also to the same h, and also there's a exact value from the analytic solution. So this is all the answer from the calculation that we already compiled in one table using the same equation. So first off, we are going to look at the Euler method with h is equal to 0.1. For x is equal to 0.1, the value that we get here is equal to 0.8 compared to the exact value that we have here is equal to 0.818751 yada yada. So this one is not so accurate compared to the exact value, but with the h becomes smaller, this one is 0.1, so we use the 0.05, which is half smaller than this one. We get 0.8100565552, which is actually a little more accurate than 0.8 only to the exact value. So same with the x is equal to 0.2 and also with the x is equal to 0.3. All of the exact value compared to the Euler method value, it's more accurate when you use the smaller amount of h, which is 0.05. So now we move to the improved Euler. For x is equal to 0.1, the improved Euler has h is equal to, for improved Euler with h is equal to 0.1, we have 0.8200400936 compared to 0.8187512213. This is the exact value. So with the h is equal to 0.05, it's more accurate than the h when it's equal to 0.1. The same thing that happened to Euler method is happening also in the improved Euler method. If we use the smaller value of h, the calculation and the value that we get for y will be more accurate. But the improved Euler method is more accurate than the Euler method itself. Same goes to the Ranch-Kutta, but among these three methods, Ranch-Kutta has the most accurate calculation. So for the h is equal to 0.05, you can see that we get 0.81875, like almost the same with the number we get in the exact value. But with the h equal to 0.1, it's slightly different with 0.181753888. This one with 13698. It's like closer to the exact value. So when the value of h is smaller, the Ranch-Kutta calculation will also become more accurate. Now moving on to the percentage of error that has been calculated with this formula. For Euler method, with x is equal to 0.1 and h is equal to 0.1, we can see that the percentage of error is equal to 2.29. So it's quite big compared to all other percentage of errors in other method. And for x is equal to 0.2 and x is equal to 0.3, we can see that the percentage is also become bigger and bigger for h equal to 0.1. But h is equal to 0.05 has proved that it's more accurate because the percentage of error on x equal to 0.1 is 1.07, which is smaller than the 2.29. But as the number of x goes increase, the percentage of error also increase. In improved Euler method, we can see that the h is equal to 0.1 with x is equal to 0.1. We can get that the percentage of error is very small, with amount of negative 0.16 compared to the Euler method. And with the h is equal to 0.05, the percentage of error become smaller than when the h is equal to 0.1. This proves that the h equal to 0.05 is like more accurate. And the range kuta is also the same. When h is equal to 0.1, the percentage of error is smaller than improved Euler and both improved Euler and Euler method, which is negative 3.15 times 10 to the power of negative 4, while the percentage of error in when h is equal to 0.05, it becomes negative 1.814 times 10 to the power of negative 5, which is the smallest percentage of error we have in here. So in conclusion, we can say that the Range-Kutta method is the most accurate method because it can get us very close to the exact value that we can get with analytic method. And also, if we want to get more accurate value, we have to use smaller h. So the smaller the value of h, the more accurate the exact value of y we're getting from the calculation. That's all. Thank you.